Greetings and welcome to lecture number 5 of Basic Circuit Theory. I am Razavi. Today we will go over some mechanics of KVL and KCL just to get comfortable with applying these principles to circuit analysis, and then go over some examples to reinforce these ideas. And these will prepare us for a little more advanced topics that we call analysis techniques, including node analysis and mesh analysis. As I mentioned before, with the knowledge of KVL and KCL and the properties of devices, we should be able to solve any circuit. So in principle, we don't even need to know node analysis. But as we see through these examples, the problem is that generally it seems that when we are analyzing a circuit using KVL and KCL, we have to go over a whole bunch of equations, try to find the right equations, etc. But nodal analysis and mesh analysis give us a methodical approach to writing the equations and solving the circuit. And that's why they are so valuable. Okay, but before we go there, let's take a look at what we covered last time in lecture number 4. So in lecture number 4, we went over KVL and KCL, and we saw that Kirchhoff's current law really is the conservation of charge. And all that means is that if I consider all of the currents coming into a node, then the sum has to be 0, meaning that in reality, some of them have to be positive, some of them have to be negative. After all, if they all bring charge into this node, then charges accumulates, and that's not possible. So we have to have some positive and some negative currents. For KVL, we said that if we go around the loop, and the loop consists of a bunch of branches that eventually come back to the same point. If you go around the loop and write all of the voltages, add them up, and come back to the same point, the result should be 0. And we introduced 2 different approaches to writing these voltages. For example, one approach is to say if we go from positive to negative, then we say minus V1. If we go from negative to positive, then we write plus V2, etc. So we just have to be careful about these signs. Okay, so for example here, I say I go down the potential, so minus V1, up the potential plus V2, down the potential minus V3, and then down the potential minus V4. And because I go back to the same point, the result has to be 0. All right, so with that, we are now ready to go through some mechanics, meaning some of these simplifying operations that we can perform before we apply our full analysis of a circuit. Okay, so these are just some tidbits that help us simplify a circuit based on our knowledge of KVL and KCL and other principles. So the first one is combining series voltage sources. So if in a circuit you see a voltage source like this, so V1, and another one like this, V2, then we know that these two can be merged into one voltage source, and so this will be equivalent to one voltage source whose value is equal to the sum of these two. So that would be V1 plus V2. So now you can see that writing the equations will be a little simpler. Now when I went from here to here, I actually apply KVL, right? Because I'm adding these 2 voltages, and that's what KVL says as you go from here to here. So 2 voltage sources in series give us 1 voltage source equal to V1 plus V2. All right, we have to be careful here that I have positive, negative, positive, negative. If this happens to be positive here, negative here, then this takes a negative sign. So again, we're following that principle that, for example, if I go this way, I go up the potential plus V2, go up the potential plus V1. All right, we have to remember that. Okay, We also have parallel current sources. So if we identify two current sources that are parallel, and by that we mean they share only one node, and the two current, they share both nodes. So that's the definition of parallel. So I have, for example, a current source like this, I1, and a current source like this, I2, in some circuit, and I see that they are in parallel because they share both nodes. So this is equivalent to the sum of the two currents. So this would be the same as just one current source equal to I1 plus I2. Okay, now what if they have opposite directions? Then what do we do? Not a problem. So suppose I have something like this. So here's I1, here's I2. Then what can I do? Well, I can say that if I didn't have I2, the current would be I1. So let's do that. Right, if I didn't have I2, I would write I1. So let's write I1. But now that I have I2, I2 is going the opposite way. So this has to be minus I2. Okay, so that's the equivalent current source. You can write it like this, or you can say I2 is here first. So I2 is going down. So this is also equivalent to I2 is going down. I have this one first. And now I come along and I add this one. So what happens? Well, this is in the opposite direction, so it has to be subtracted. So minus I1. So these two are the same. Why? Because we change the direction and we multiply it by a negative sign. Okay, the next principle are other devices in series or parallel. So for example, resistors in series or in parallel. So if we identify some resistors in our circuit that happen to be in series or in parallel, we can merge them so that we can simplify the circuit. So when we see a complex circuit, our first reaction should be to apply these mechanics, these principles, to simplify the circuit before we sit down and write equations, before we write the final KVLs and KCLs. Okay, so with these, we can go over some examples just to see how these come together. So let's change the color and look at this example here. Suppose I have something like this. I have a voltage source on one side, which I call V1. And then I have, let's say, two resistors. I have R1, another voltage source here, plus a V2, another resistor here, R2, and another voltage source here, V3. So that will be our overall circuit, V3. Okay? All right. So first of all, I would like to find the current that flows through this entire circuit. There's only one current, right? Some current starts from here, flows this way, and comes back. So let's try to find that current in terms of all the known quantities. Okay, so we'll just call that I1. And what we know is the following. I1 flows through R1, generates a voltage according to Ohm's law. So that voltage would have a polarity as follows. So let's change the color of our pen to purple maybe. So it would be plus here and minus here. This would be I1 R1. How do we know that? Because the current has to go from high potential to low potential for Ohm's law to be valid. Ohm's law says V is equal to IR. Right? Ohm's law doesn't say V is equal to minus IR. So to make sure that we are writing the equation correctly, we have to make sure that the current goes from high potential to low potential. So this is high potential, this is low potential, the current is going this way. That current times this resistor gives me that potential. So that's I1 R1. Okay, then here I1 continues to flow, so we can draw it on this side, you can draw it on this side, same thing. So I1 is coming in, and again, it has to go from high potential to low potential. So high potential, I put the plus sign here. Low potential, I put the plus sign here, minus sign here, and I have I1 R2 as the voltage drop across that resistor. Okay, so now I don't know I1 yet, but I have found all of the voltages in terms of I1 and other known quantities, so I can go ahead and write a KVL around the loop. Let's go ahead and do that. So KVL says you start from a certain point, and we just keep adding these voltages very carefully until we go back to the same point. And then we equate the result to 0. So let's go from here and start writing our equations. So again, we want to go with one convention or one approach. We say going up the potential, we say plus V1. Going down a potential, we say minus I1 R1. So let's do that. So we're going to write plus V1 because we're going up the potential. Here we're going down the potential from plus to minus, minus I1 R1. Now here we're going from high to low, so minus V2. Here we're going from high to low, so minus I1 R2. And then finally going from high to low, minus V3. I am at the initial point, right? Because these are just connected by a piece of wire. So this node and this node are only one node. So the result should be 0. Okay, so now we can find I1 in terms of all the known quantities. So I1 is equal to, I have V1 minus V2 minus V3. So V1 minus V2 minus V3 divided by R1 here and R2 here, so that's R1 plus R2. Okay, so that's simple enough. But we also observe something interesting. We see that the final current that we obtained is in terms of one giant voltage divided by one giant resistor. So it is as if you just had one voltage applied across one resistor, right? It is as if you had this, as if we had a single voltage source equal to V1 minus V2 minus V3 applied to a resistor equal to R1 plus R2. This current is still I1 because that's what Ohm's law tells us, right? Ohm's law says that this voltage divided by this resistor gives us this current. So if this voltage is V1 minus V2 minus V3 divided by R1 plus R2, it gives us the same current. So interestingly, this circuit and this circuit are equivalent. Why is that? Well, because what's happening is that this voltage source and this voltage source and this voltage source are actually in series. It may not be obvious at the first glance, but they are. How do we know that? Well, because they have the same current through them. You see, the current flows, whatever current flows through V1, also through V2, also through V3. And in fact, R1 and R2 are also in series because they have the same current, even though they don't share a node, right? So if I redraw the circuit, you will see it better. So we're going to draw it like this. We'll say V1 is here. That's V1. Let's move V2 from here to here. So V2 is like this. And then let's move V3 from here to here. So then we have V3 plus minus. And then we have the two resistors, R1 and R2. And then we go back to where we started. This circuit is equivalent to this circuit. How do I know that? Well, because this circuit is equivalent to this circuit. How do I know that? Well, because this voltage, you see, I have V1, but I have to subtract from it V2 and V3, right? high potential to low potential. So this whole thing here is the same as that. And then these two resistors are the same as that. Now, we proved that this was equivalent to this. We can see that this is equivalent to this, therefore this is equivalent to this. And that shows that these three voltages are in series, and so are these two resistors. So it's very helpful by looking at the circuit, trying to identify these series and parallel combinations so that we can quickly simplify the circuit. All right, let's go ahead and look at another example here. Let's see. Okay, I go to this green color maybe. Okay, in this example, we have a couple of current sources. We actually have 3 current sources and 2 resistors. So here are our current sources IX, R1, IY, R2, and IZ. Okay, so we have 3 current sources and 2 resistors. Now, we could write KVLs and KCLs and so on, but before we get there, let's try to see if we can simplify the circuit using these principles. Now, let's look at the current sources. What can I say about IX, IY, and IZ? IX and IY are in parallel because they share these nodes. You see, IX and IY share the same node. Again, remember, this is just a big piece of wire, and that piece of wire acts as a short circuit. So all of these constitute only one node, and so do these. All right, so IX and IY are parallel because they share these terminals and these terminals. And how about IZ? Same thing. IZ also shares the same terminals with IX and IY. So I can write this result as, imagine for a moment that we did not have IY and IZ, we had only IX. Okay, so that's IX, right? Okay, IY flows in the opposite direction, so I have to subtract it. So minus IY. And then IZ opposite flows in the same direction as IX, so we just add it. So plus IZ. That is the equivalent of these 3 current sources. All right, how about R1 and R2? They are also in parallel because we can see that they share these terminals and share these terminals. So I can just write that here as we have the symbol R1 in parallel with R2. Sometimes we write it like this. If you want to be more specific, you can write the result, which would be R1, R2 divided by R1 plus R2. So this is the symbol we use to indicate that 2 components are in parallel. So you can see that suddenly the circuit becomes much simpler. For example, if I'm interested in this voltage difference here, so let's call this voltage difference Vx, then we can readily find that because I have a current flowing this direction going through this resistance. So because the current is entering from the high side to the low side, I can write Ohm's law. I can say that Vx, this voltage, divided by this resistance over R1 in parallel with R2 is equal to the current that flows through the resistor, and that current is this. How do we know that? Because we are actually writing a KCL here. We're saying that any current entering has to be equal to any current exiting. So that current is Ix minus Iy plus Iz. So readily it gives us Vx is equal to this current times this resistance. Okay, so that's the solution of the circuit if we are interested in this voltage difference. And once we have this voltage difference, we can find everything else. If I'm interested in this current, I divide that voltage by this resistor. If I'm interested in this current, I divide that voltage, this Vx, by this resistor, etc. All right? Okay, so these are some examples to show how KVL and KCL work together to allow us to solve any circuit that we are given. In solving these circuits, we always have to remember that resistors satisfy Ohm's law, current sources want to push their own current, voltage sources want to impose their own voltages. Based on these, we can always write KVLs and KCLs and solve the circuit. All right, let's look at another example, which is a little more complicated. Let's see here. Okay. So suppose we have a current source that is independent, so we call this Ix, and then we have a resistor here, R1, and another resistor here, R2. Okay, these are all connected. And then we have a dependent current source. So here's a dependent current source. And the value of that dependent current source is given by K times I1. So I'm going to call this current here I1, which we don't know yet. But I will say that this current source, if you want to call it IY, has a value of K times I1. So remember that a dependent source can depend on a current somewhere or on a voltage somewhere, right? It doesn't matter. So in this case, this current source decides to imitate this current, whatever flows here, but multiplied by a factor of K. K could be higher, positive, negative, 1, greater than 1, less than 1, whatever we want. Okay, so our objective is to solve the circuit, and by solving we mean we want to find all of the voltages and the currents in the circuit in terms of the known quantities. The known quantities are I1, Ix, R1, and R2, and K. Okay, so how do we go about doing that? Well, let's eyeball the circuit for a moment and see what we can do here. Okay, so let's call this current I1. We have to deal with it anyway, right? In fact, if we can find I1, that would be great, because once I have I1, I can find everything else. So let's say I1 is unknown. All right, if I1 flows through R1, how much voltage do we generate from here to here? Ohm's law says it will be I1 times R1. And Ohm's law says that equation is valid if the current goes from high potential to low potential. So the potential difference I have to assign here, or the voltage drop, should be of this form. So it will be plus here, minus here, because the current has to go from high potential to low potential, and its value will be I1 times R1. I don't have room here, so I'm going to write it over here. I1 R1. All right, so that's the voltage difference across R1. How much is the voltage difference across R2? It's the same thing, right? Because these two resistors are in parallel. They share these terminals, they share these terminals. So whatever voltage we have here, we must have here as well. So because the voltage drop across R2 is the same as this value, I can find the current through R2. So the current through R2 will be this voltage, this value, divided by R2. So that current is given by I1 R1, this voltage difference, I1 R1 divided by R2, Ohm's law. So far so good? Okay, so that is the current flowing through R2. Now whether you put the arrow here or here doesn't make any difference so long as the direction of the arrow and the polarity of the voltage are consistent. All right, so that's great. We found the current through R1, or we have the current through R1 called I1. We found the current through R2. So it seems that now it's a good opportunity to write a KCL at this node. Because this current is Ix, this current is I1, which we are looking for. This current is I1 R1 over R2. and then this current is KI1. So let's go ahead and do that. So for example, I can say, remember we had different ways of writing KCL. One is we add up all the currents that are entering and equate the result to all of the currents that are exiting. So for example, here IX is entering. So IX is coming to the circuit. Let's see here, IX. And then all these three currents are leaving this node, right? This one is going down, this one is going down, this one is going down. So we can write here I1 for the first one, plus this one, which is I1 R1 over R2. And then finally, KA1 plus KI1. Okay, so now I can see that we can readily find I1 in terms of IX and the other parameters, right? So that gives me I1 is equal to IX divided by 1 plus R1 over R2 plus K. So we have 1 plus, let's see if this pen works here, plus R1 over R2 plus K. So I hope you can read what I wrote down here. So 1 plus R1 over R2 plus K, that's the overall result that we got for I1. Okay, and now once I have I1, I have everything else. I2 is just I1 times R1 over R2. We can find that. This voltage is I1 times R1. We can find that. And the circuit is completely solved. All right. So we're just going through examples, trying to apply our knowledge of KVL, KCL, and Ohm's law, just trying to see how we solve circuits. What you have seen so far is that it seems that my approach to writing these equations is rather haphazard. It seems that I'm just sort of picking some equations from different places and writing them down, trying to solve the circuit. There doesn't seem to be a simple, methodical approach that I could follow step by step. And that's why eventually we want to get to, for example, node analysis, so that writing these equations does not become guesswork. It just follows a simple routine. All right, so let's go over another example. So I have to go to the next page here and look at our next example that is also a little more complex. Okay, so let's see here. We have something like this. We have 6 amperes of current going this way. And then we have a bunch of connections here. So we have this resistor R1, this resistor R2. Okay. And then we have a dependent current source going this way, going up. And then we have these 3 resistors that look like this. And then we have another current source that's flowing downward. Okay, so it's a little complicated. I have to assign names or values to all these things so that we can write equations. So let's just call these, so we'll call this I1, so don't even worry about this value. And then this current source is a function of this current here. So we call this, so let me call this IX, let me call this I1, and then this is K times I1. So similar to previous example, except that this current source is pointing upward. It follows this current and multiplies it by K and makes it flow upward. Okay, and then we have For example, R3, R4, R5, and then IY. Okay, so it's a big jumble of devices. Does this really happen in practice? No, not really. This is not a representation of circuits that we see in practice. So why do we go through it? Simply because we're trying to hone our skills with KVL and KCL and these other principles. Right? So we want the circuits to be gradually more and more complex so that we have enough understanding and enough insight in writing these equations. Okay, so again, we want to solve the circuit. What are known are Ix, R1, R2 through R5, Iy, and K. And what's unknown is, for example, I1 and everything else. So we can try to find I1 first and then go from there, find everything, all other quantities. All right, so how do I go about solving the circuit? Well, similar to the previous case, I will start from here. I have a current of I1 flowing from top to bottom through R1 and generating a voltage according to Ohm's law. So let's go ahead and denote that voltage. The voltage has to have high here, low here, and its value is given by I1 times R1, as we saw in the previous example. Okay, that's great. How about the current through R2? Well, from the previous example, we know what happens. Because these two are in parallel, and because this has a voltage of I1 R2, so that's this one. So I take the voltage I1 R1, I take the voltage I1 R1 divided by R2 to get the current. So this current is I1 R1, meaning this voltage drop, divided by R2. All right, okay, so we got that. Now, because this is K times I1, so that is known, that's K times this current, which we're trying to find. And how about these three? What do I do with these three? Well, I can see that R4 and R5 are in parallel. They share these terminals, they share these terminals. And then R3 is in series with this parallel combination. So in my mind, I can just replace this whole thing with a single resistor. We can call it the equivalent resistance. And that equivalent resistance consists of a picture like this. R3 and R4 in parallel with R5, right? So that's what's happening. So now, can I find the current through this circuit? Sure, because the voltage drop that I have from here to here, I1, R1, is present everywhere. This is a giant piece of wire connecting all these nodes, and so is this one. So this is just one node, and this is one node. Remember that an ideal piece of wire does not have any voltage drop across it. So whatever voltage we have here, we also have here, we also have here. So this voltage difference of I1, R1 is present here, and present here, meaning present here. If I divide that voltage difference by the resistance, I get this current. So let's write that current. That current, I just put an arrow here, would be this voltage, I1, R1, divided by this resistance. So we'll just write that as R3 plus R4 in parallel with R5. Okay. All right. So now it seems that we are ready to write a KCL at this node. We have all the currents, right? We have Ix going in. We have this, and this current flowing out. We have this current flowing out, and we have this current flowing in. So let's try to write a KCL. So we're going to write all the currents that flow into the node. That would be Ix is flowing into the node. This one is flowing into the node, so plus KI1. We don't have anything else that's flowing into the node, so this will be equal to all the currents that are coming out of the node. So that would be I1 here, plus this one, I1 R1 over R2, plus the current through this branch, which we found to be this much. So plus I1 R1 over R3 plus R4 in parallel with R5. And then finally, this current is also flowing out of the node, so plus IY. Okay? And now we can write I1 in terms of everything else. So we have I1 here, factor it out. So we can say I1 is equal to. So let's say we take this one to the other side, and we take this one to this side. So we have IX minus IY divided by 1 plus R1 over R2 plus this minus K. So we have 1 plus R1 over R2 plus R1 over R3 plus R4 over in parallel with R5, and then finally minus K, this K comes to the other side. So that's the current I1. Now from I1 I can find everything else, right? Because we already have equations for these. This current is just I1 scaled by R1 over R2. This current is like this, etc. So we have everything that we need. Okay, so a few notes about what we have done here. Number one, you might say that R2 and this general combination are in parallel. That's true. So I could have actually combined these further. I could have said that let's move this over here and just write it as R2 parallel with this combination. We could do that, sure. And in fact, you can barely see that here. If you cross multiply these, you see that R2 does become parallel to the structure. But I figured this is okay. We don't have to do that combining. There's not much simplification in the mathematical labor. Now let's go one step further and ask, can I combine R1 and R2 into parallel combination? Because they are parallel. Well, no, there's a problem. So let's go ahead and do that and see what happens, right? Let's go ahead and change the color to green. So if I combine these two into one resistor and call that R1 in parallel with R2, that is correct, of course, but the problem is that I have lost I1, right? I1 flows only through R1. Once I combine these two, I cannot say I1 is here anymore, right? Because this is the parallel combination. If I lose I1, then I lose this one. This is dependent on only I1, only the current through R1, not the current through R1 in parallel with R2. Then I lose this one, then I cannot solve the circuit. So we have to be careful about these combining actions because we don't want to lose controlling parameters, right? This parameter controls this parameter. If we lose it, then this guy is lost. He just doesn't know what to do. Okay, so that's another interesting point that we observe here. I think we are now ready to move to node analysis. We have some time today to talk about node analysis, and of course, we'll pick up next time. So let's talk about node analysis. Okay, so as I mentioned before, our objective is to come up with a simple step-by-step procedure that can be applied to any circuit. Yes, we will be still applying KCLs and KVLs, but at least we don't want to think whether I am writing all the equations that I need, am I missing some equations, do I have too many equations, etc. So we want to have that a nice and simple procedure. All right, so node analysis goes as follows. If I am given a circuit, I will perform some actions on the circuit itself, and I follow certain steps so that I end up with a bunch of equations. And then I solve these equations, and then I'm done. All right, so let's say we have some sort of circuit like this. Just as an example, it can be anything that we have. Okay, something, doesn't matter. So we have this big circuit. This big circuit has all sorts of things. Of course, voltage sources and current sources. Could have something here, etc. Okay? All right, and we want to solve the circuit. So the first step in this process is to assign a node, one of these nodes, to be the reference node. So we say step 1, select a reference node, and sometimes we call this the ground. It doesn't mean that it is literally connected to the ground. It's just a name that we use to identify this particular node. So which one should be the reference node? It doesn't really matter. In most cases, we would like the node that is the most crowded, meaning it receives the most branches, to be the reference node. But you can select any node that you want. We just have to pick one node and call it reference. So for example here, let's call this the reference. And I need to some sort of notation so that visually it's clear. My notation will be this. We have this symbol, which is the symbol for ground. So sometimes we also write it as GND. GND stands for ground. You can call it the reference node, you can call it the ground, whichever you want. That's the first step. All right? Okay. In the second step, we go ahead and assign voltages to all of the other nodes of the circuit with respect to ground. Remember, a voltage is always measured between two nodes. Now, what I will insist is that we assign the voltages, we define the voltages to be from every node with respect to ground. So, I will call this, for example, VA. What does this mean? It means that if I take a voltmeter and put it between this node and this node, I'm going to measure VA volts. Okay, so this is measured with respect to here. For every node, we'll do the same thing. So here, we call this VB. And VB, again, means that if you put a voltmeter between here and here, we will measure VB volts. So all of the nodes that we have, we will assign voltages to those nodes. All right, so VC, etc. Okay, so we say assign voltages with respect to the ground to all other nodes. Okay? All right. So, one quick question. If this circuit has n nodes, how many of these voltages will we have? We will have n minus 1 because 1 is already ground, right? So that means that we'll have n minus 1 node voltages because 1 is already taken and called ground. So let's just say that this circuit has n nodes. Okay? So we have n minus 1 node voltages. We haven't found them yet, but we call them, right? VA, VB, or V1, V2, all the way to Vn minus 1. All right. Now we have to follow a few more steps. But because we are running out of time, I will defer that to our next lecture. I will see you next time.